In this video, we're going to consider an application of the Heaviside function, or a discontinuous 0-1 switching function. We derived a couple of Laplace transforms that will need learning, importantly, that although the Heaviside function is discontinuous, the Laplace transform is continuous in the S domain, which is extremely convenient. We don't have to worry about breaking things apart into its pieces. We just get to operate with continuous functions at all times. So let's take a look at an example. For a drug utilized in emergency hospital settings, such as morphine, doses are extremely critical. It is known that morphine has a half-life of 1.5 to 7 hours, and that a concentration of 2 milligrams per liter is likely in a setting involving anesthetics, including any situation involving incisions and or surgery that would normally be painful. Assuming a half-life of about 4 hours for a person with 5 liters of blood, we know that about 17% of the amount of drug is filtered out of the bloodstream each hour. Assume the following. 7 milligrams will be added continuously over the course of an hour. This will be done for 1 hour, at which time the dosage will be adjusted to 4 milligrams. Write a differential equation that describes the rate of change in milligrams per hour of morphine. I'm going to start off by drawing a tank model diagram, or a bathtub model, where we can indicate what's coming in and what's going out. While we do that, we want to make sure we define our variables. Y will be the number of, or we'll just say the quantity, amount of morphine in the bloodstream. After, well, since we're in hours, we'll just say after T hours. Okay, and because we know that about 17% is filtered out each hour. So that's probably the first thing that I'll start with. What in terms of morphine is exiting the body? Well, 17% of whatever is inside the body, which is or in the bloodstream, which is Y. We didn't use units here. We should probably use units. Y milligrams. 17% of those Y milligrams will exit each hour. Keeping in mind that dy dt will have units of milligrams over hours, or milligrams per hour. Okay, so 17.17 Y milligrams per hour exit the bloodstream. Now, what's coming in? Well, it depends on the time, right? Well, maybe we'll write it like this. We'll write 2 arrows in, and this one will be 7 milligrams per 1 hour, but this will only be over a domain, over the course of an hour, 1 hour. So this is between time 0 and 1. At which time the dosage will be adjusted to 4 milligrams. Okay, so I'll draw another arrow coming in. I'll use a different color here to distinguish them. There will be 4 milligrams per 1 hour coming in, but that will be for time greater than or equal to 1. Up until we stop doing it altogether. All right, so the problem is, of course, that we have this constant 7, but that's only between time 0 and time 1. What we learned is that we could actually cause things to turn on and off. In our previous example, if we take the lower of the time minus the Heaviside at the higher of the time, then 3 minus 2 will give us that 1 hour period where we're infusing at that rate. What we want is graphically, maybe I'll do it graphically first. And I'm just doing this for the rate in. So this is going to be the milligrams per hour on this axis. And on this axis, it's going to be as a function of hours, right? Because how many milligrams per hour we're putting in depends upon the time. So 1, 2, 3, 4, 5, 6, 7. From time 0 to time 1, we want to be infusing at a rate of 7 milligrams per hour. I'm going to put an open circle there at time 1 since we're going to stop that infusion there. And then we're going to drop this down to 1, 2, 3, 4. And then it's going to remain at 4 milligrams per hour for as long as the doctors decide. Well, I want to start something at 1, and I want to then turn that off at time 1. Okay, so let's just imagine this actually as two separate functions. The first one, I'm going to go over this in, let's say, aqua. We really want this, and then we want, as for that function, to return back to 0. So we kind of want the opposite. We don't want it to go from 0 to 1. We want it to go from 1 to 0. Well, the Heaviside function, recall, takes on a signal of 0 until that time and then switches to a 1. Now, if I play a little bit of mathematics here and I take 1 minus u sub a of t, if I did 1 minus u sub a of t, what would that look like? Well, up until time a, u sub a would be 0, and 1 minus 0 is 1. So if I do 1 minus 0, I'll get 1. And then for time greater than or equal to a, well, u sub a takes on a value of 1. However, 1 minus 1 is 0. So by doing 1 minus the Heaviside, I can actually switch the order in which the zeros and ones occur. So what I'm going to have here is I am going to have 1 minus u sub 1 of t, and I want to take that whole thing. That's just going to be my switch. That goes from a 1 to a 0, but I don't want it to go from a 1 to a 0. I want it to go from a 7 to a 0. Well, it's easy to do that if you just multiply by 7, because it's 7 times 1 up until time 1, which is 7. And then it's 7 times 0 for time greater than or equal to 1, which is 0. Now let's think about this second piece of the puzzle. We want, for the second infusion, we don't want to have the 4 milligrams infused for the first hour, but then we want the 4 milligrams to be infused thereafter. Well, that's just your standard Heaviside function. So we're going to have plus 4 times the Heaviside. Well, it's going to be the Heaviside at time 1, right? These are both going to involve time 1, because you can think about 1 as being on and then turning off at time 1, and the 4 milligrams being off until time 1 and then turning on. So that makes the mathematics a little bit easier to deal with, is to break it up into 2 simple Heavisides. So this will ensure that I have 7 while time is less than 1, and then after time 1, the 7 milligrams will turn off, will return back to 0, and then U1, remember that U1 here and here turns into a 1, but because we did the 1 minus, this is going to give us a 0 for time greater than or equal to 1, but 4 times positive 1 will give us 4. And then finally, I am going to subtract away the outflow rate, which is that 0.17y. Great. So let's simplify this a little bit. Dy dt, if I distribute that 7 through, I'll have 7 minus 7 u1 of t. And you can do that. This is the reason we wrote it this way, is because logically it made sense to write it that way. And then I have 4u1 of t minus 0.17y. Well, notice that these two terms right here, collectively, those will give me negative 3u1 of t. Remember, u1 is just a function, just a variable for all intents and purposes. And now I just have to worry about solving the differential equation, dy dt equals 7 minus 3 u1 of t minus 0.17y. With initial condition, y of 0 equals 0. Okay, so we assume that the person does not have any morphine in their bloodstream at the start of infusion. So now we can use Laplace transforms. Laplace of dy dt, and I'm just going to kind of do this, I'll just say it, the Laplace of dy dt and the Laplace of the right-hand side. That's going to give me s Laplace of y minus initial condition equals the Laplace of 7 over s, minus 3 times the Laplace of u1. Okay, wait a minute. What's Laplace of u1? Oh, Laplace of u1 will be e to the negative 1s over s. Perfect. E to the negative s over s. And then we know that the Laplace of y we can't find because we don't yet know what y is. It's some function of time. So we just write it as the Laplace of y. We begin rearranging, so move over the add 0.17 Laplace of y to both sides. Then we'll have s Laplace of y plus 0.17 Laplace of y, which is s plus 0.17 times the Laplace of y if we factor that out. And then I'll have 7 over s minus 3e to the negative s over s, plus moving the initial condition over. Well, that's just going to be plus 0, right? This is equal to 0, so I guess I don't really have to worry about that at all. And now I can do my division, and I'll get the Laplace of y is equal to 7 over s times s plus 0.17. We know what to do there. That's going to have to be partial fraction decomposed. Minus 3e to the negative s over s times s plus 0.17. Now, we do have a function in the numerator. We'll either write this one of two ways. We might just write this as 3e to the negative s times 1 over s times s plus 0.17, and then just do partial fraction decomposition on that. Because maybe the technology, if we're using technology, the technology will not like that e to the negative s in the numerator. But let's find out. So before we do any inversion, we just want to make sure we split these apart because we see the need for it. And here I already have partial fraction of 7 over quantity s times s plus 0.17. Comes out to 41 point, I'm going to round it to 18, 41.18, 41.1, we'll just leave it as exact, why not, 1765 over s, and then we have minus the same thing over s plus 0.17. Okay, now we want to do this term, and I think that's where we're going to bump into a little bit of a challenge. I'm going to do minus 3, because I know I'm going to forget my sign if I don't do it. E to the negative s. Let's see what it does there. It may, it's not going to like that, unfortunately. So leave the negative 3 there, and let that, remember that we're going to need that e to the negative s. The reason I'm putting that negative 3 in there is I won't have to worry about multiplying in 3 later on. So what I'm going to do is I'm going to write plus e to the negative s times, and remember I just did negative 3 over that, which comes out to 17.6471 over s plus 0.17 minus the same thing over s. Okay, so we know how to invert these first two terms. This first term right here is going to invert into, well, what we know that the inverse Laplace of 1 over s is 1. So this is just going to end up being a constant term. This right here is going to invert into, I'm going to put the minus sign there so I don't forget, 41.1765 e to the negative 0.17 t. Over here is where we're going to bump into a little bit of a challenge. Now I'm gonna go ahead and just factor out this 17. Oh, maybe I won't. Maybe I won't. See, I change my mind all the time. Okay, because I have this e to the negative 7 multiplying this, this is actually going to require us to utilize the second operation here. We have something of the form e to the negative as times the Laplace of some function. So this right here is already the Laplace of some function, right? The question is, what is f of t? What is the function that we would have to Laplace to get this? Well, that's pretty straightforward enough. That's going to be 17.6471 e to the negative 0.17 t. And in order to work backwards, I need two things. I need to know what is f of t, because here I'm just going to replace the t's with t minus a. And that begs the question, of course, well, what is a? Well, a is negative 1, right? That's still the same a that we had originally. So that's usually an easy one to deal with. A is negative 1. And now we can invert this. We know that to invert that whole thing, it's going to be u sub a, so u sub 1 of t, times the function with t minus 1 plugged in. Okay, so f of t, I'm sorry, a is not negative 1, a is positive 1. It's e to the negative as. So a is the opposite of the sign of what's in the exponent. So this is just 1. So f of t minus 1, well, just how we know function notation means whatever's there is what you plug in up here. So this will be 17.6471 e to the negative 0.17 times t minus 1. Okay, so that's just that exponential function, e to the negative 0.17 t, shifted over 1 unit. And that should make sense because there's a component that won't be decaying until time 1, and that's going to be the 7 milligrams that we put in. And, okay, same kind of idea here. This is the Laplace of some function. Again, remember that this distributes through, so it actually affects both terms. Question is, what is that function? Well, this is the Laplace transform of just 17.6471. It's the constant. The inverse of that is a constant. A is still 1, right, because it's still at e to the negative as. And now, for a constant, since it's always the same, shifting it to the right isn't going to change it at all, right? The constant function, if I take that, I say, hey, shift this infinitely long function, shift it over a couple of units this way, well, it's still going to be the exact same function. It doesn't change. It doesn't have any rate. It has 0 rate of change. So there's nowhere to plug in t, in other words. 17.6471 is that f of t minus 1. All right, putting it all together. Putting it all together, now we invert, and I'm kind of just saying this out loud, we invert both sides. We already know this is 41.1765 minus 41.1765 e to the negative 0.17 t. Now, to put our work into action here, recall that this is going to be the Heaviside times f of t minus a. So, plus the Heaviside, a is 1, so u1 of t, times f of t minus 1, which is 17.6471 e to the negative 0.17 times quantity t minus 1, plus, again, the Heaviside, you could factor out the Heaviside if you wish, u1 of t times f of t minus 1, which is just 17.6471. So there is our solution in its complete form. And now the question is, using graphical support of the solution, will the amount of drug reach the desirable level so that surgery can place at the 2-hour mark? Well, wait a minute, what is the desired level? It is known that morphine has a half-life of 1.5 to 7 hours and that a concentration of 2 milligrams per liter is likely in a setting involving anesthetics. Okay, well, this person has 5 liters of blood, so it's 2 milligrams per liter, 2 milligrams per liter, and that's per liter of blood. 2 milligrams concentration per liter of blood is how drugs usually work, times 5 liters of blood. Well, that's going to give me a total of 10 milligrams. So my target is there a time at which y equals 10? All right, we're going to graph this, and I'll show you how to do this in Desmos. We actually have to define the Heaviside function first. Okay, so I'm going to come in here and I'm going to define a function. I'm just going to call it u1 of x. Okay, I'm going to use function notation. Right now it's asking me do I want to insert a slider for it, but once I put in the equal sign and I start typing, it'll all work out. So what we want is we want curly brackets. And first of all, we say for x less than 1, actually we want for x, we could just do less than 1. You could also say 0 less than, yeah, we'll just say x less than 1. Plot, so comma, now tell it what to plot. You want a 0. And, oops, sorry, we want a colon there and then a 0, okay? So notice that all it's doing is it's plotting for x less than 1, it's just plotting the 0 function. If you wanted it to be between 0, do 0 less than or equal to, and then it'll just plot that piece of the function. I think I'll leave it like that. And to get the less than or equal to, I just type the less than sign, press the equals button, and it automatically does that. Okay. Now I want to do another function, so I'll do a comma, and I'll say for x greater than or equal to 1, comma, or colon, plot the function 1. There it is. We've got a Heaviside plotted. We don't actually want that Heaviside plotted. I'm just defining that so that we can type it into our solution formula. So what we have is 41.1675, minus the same thing, e to the negative 0.17x. All right, nothing interesting too far. That's just, getting some infusion going on there. And now we need the Heaviside. Now we'll have u1 of t times this function here, 17.6471. So let's say plus u1 of x. Now notice you get this weird break here. That's because at time 1, we're adding 1 to it, so it actually just creates a break in the graph. But don't worry about that yet. 17.6471 e, a little bit of trouble here toggling, e to the negative 0.17 parenthesis x minus 1. Okay, it's not quite complete, but you can see we're getting this broken looking graph here. No! Oh, there we go. Okay, all kinds of panics today. Now I'm going to do, it's a, we had a minus sign, so this is going to be a minus. Let's just check our signs real quick. That should be a minus sign because here we had a minus sign. Okay, so we'll have minus there. So I should have done that same thing here. I should put the minus sign in front of it. Minus u1 of t times 17. Times that guy there. Okay. So nothing looks super interesting until you start to zoom in a ways. And you see that, first of all, over the course of the first hour, Okay, there's time 1. Let me actually just plot the line x equals 1. And all I'm doing here is just plotting the line x equals 1. In fact, let me just change it to dotted, just for reference. So that's where the infusion of the 7 milligrams per hour. Notice how steep that curve is right there. It looks like a line, but actually, if you defined it for a longer period of time, then it would actually look like this exponential graph here. But because we lower the infusion rate, notice how the rate of change also is a little bit lesser than it was back here. So that's where interesting stuff happens. And now we want to know, will we hit 10 milligrams after 2 hours? So let me actually define this as y, or f of x equals, and let me just calculate f of 1. Okay, so f of 1, I'm just going to actually have it plot the point, 1 comma f of 1, click label. We're actually only at, oh, that's time 1. We want time 2. So time 2, we're actually at 9.109 total milligrams of morphine in the bloodstream. We wanted to have 10, and therefore no dice. We're not quite ready to infuse, to start surgery. All right, so in conclusion, we have to say here that no, only 9.1 milligrams present.